So let's see, got it. Just want to get this going. So this is the end of week 2, right? So during week 1, we only had enough time together to kind of go through the orientation. So that's what we did last week on Wednesday. And then just to kind of like, save face a little bit, we on Monday of this week, let me go ahead and get these guys. Gonzalez, A, B, C, D, E, F. Here he is. And this one, okay, I saw him too. Cool. Come here. Come on. Thanks. Ooh. You smell like outside. Let me see. So many distractions going on. I don't know who that is. Oh, I do know. I saw him. Hang on. Where is he? It's not that one. Vander Acker. There he is. That's an interesting name. Is that like German or something? Okay. We are streaming. Let me share my screen. And let's hop over here. So we'll start here. Okay. So just as an update of where we are, let me see. So this is the end of week 2, right? So, during week 1, we only met for one day. So we only had enough time to go through the orientation together. So then this past Sunday night at 11:59, weeks 1 assignments were due. That was like 1.7 inverse functions. And so really during week 2, we wanted to start working on 2.5 rational functions. So that's what we'll be taking some time to go through today. I'll go through as much as the presentation or the lecture as I can. Keep in mind that the lecture portion that I'm going through is already available on my YouTube. So I think I made that playlist available that has all the pre-recorded lectures. Also, as usual, this is remote asynchronous. So once you've gotten your attendance credit, which everybody, I think in my roster today, everybody got their attendance credit, you're not obligated to stay. Because I am live streaming these sessions on my YouTube, so you can watch them at your leisure. The main thing that I need, the main task that I need from you all is basically each day to get your attendance credit, again, which you've successfully done today, and then just get your assignment submitted on Pearson. I do encourage you all to work together. I don't know if you have a group meeting going or not. I know in the past students have done that. I think it's a great idea. I think it mimics life more so, like, because obviously when you're in the world, you're gonna be able to collaborate a little bit, you know what I mean? So you want to do what you can on your own, but then I think collaboration is important. I feel like less of competition and more of collaboration. I feel like when the more people that collaborate, the better it is for everybody, right? I mean, that's going forward. That's just my personal philosophy in life. Competition, I mean, it's great, and you do kind of like weed through people, but then you kind of like overlook people, and because they don't necessarily win the competition, you think they don't have value, where in reality, those people that you overlook a lot of times hold the key that everybody needs to transform the whole game, right? So everybody's perspective is important. Every piece of the puzzle is important. You can't have a complete picture of missing pieces of the puzzle. Let's see. And also, as usual, if you have questions or if you have requests, feel free to either unmute yourself or type it in the chat. I do check the chat periodically, and I'll check attendance again in about 15 minutes, in about 5 minutes or so. So let's take some time to start making our way through chapter 2. So last time we did 1.7 on inverse functions, and today we only have one section in chapter 2 on polynomial and rational functions, and so we're going to be looking at 2.5 rational functions. A few objectives here. We like to define what we mean by rational function. We like to define vertical and horizontal asymptotes. We like to graph translations of the function, the reciprocal function 1 over x. We like to find vertical and horizontal asymptotes of any, graph rational functions with oblique asymptotes, and graph a revenue curve. Now, I'm not sure if that's asymptotes or asymptotes. I always like stammer over that, but you'll get the concept. Basically, you'll see what an asymptote is momentarily. Yeah, okay. So can I get a volunteer to read this slide on rational functions?
Sure, I can do it.
Okay.
A function f that can be expressed in the form f of x equals n of x over d of x, where the numerator n of x and the denominator d of x are polynomials, and d of x is not the zero polynomial. It's called a rational function. The domain of f is all real numbers in which d of x does not equal
I was literally pressing about what this thing was.
Let's see. Just mute everybody. I know there's a quick. Cool. And let me get the student as well. Since I see him, there he is. Got him, coach. And let me check the chat really quickly. I see a notification there. Let's see. Yeah, I don't know. That's up to you all. The question is there a group me? There may or may not be. I encourage it for you guys to communicate. I think it's a great idea. I've had good experiences with that in the past. Yeah.
Did you mark me down for attendance?
Yeah. So as long as you make it into my Zoom, like as long as you get into the because I let you guys in one by one. So as long as you're in the session, that means you got your attendance credit. And if I don't say anything, that means you've gotten your attendance credit. Yeah. Okay. Let me see. A function that can be expressed in this form, right, where the numerator and denominator are polynomial functions or expressions where the denominator is not the zero polynomial, right? So a rational function is like a rational number. It's basically like a fraction where the top and the bottom are polynomials. And a polynomial is basically a finite sum of monomials, right? And a monomial is basically like one term where you typically have a real coefficient times some variable x with to some integer exponent, right? And you'll see it. Once you identify what a monomial is, like one term, which is fairly simple, then a polynomial is just a finite sum of monomials, right? You'll see that and you'll get it. It'll become kind of clear, right? So in each of these, we're asked to find the domain of each rational function. So in general, for a rational function, for all of these, in general, the domain is all reals except, what do you think we have to throw out? Whenever we're dealing with fractions, we cannot do what? Whenever we have fractions, we cannot divide by
zero.
Can't divide by zero, right? So in general, so this is similar. In general, the domain for a rational function is all reals except any x that makes the denominator zero. So long story short, we got to throw out any x that makes the denominator zero. So like if you look at the first one, what value of x makes that zero, makes the denominator zero in part A? Right? Because if you set the denominator equal to zero, if you say x minus 1 equals 0, that means when x is 1, that's going to make the denominator 0. For the second one, we need to factor. I think I'm going to rely on the type notes because it's not too, we're going to get more practice with that. And for C, you can quickly look. Actually, maybe I should write these out. Let me see. If we factor that out, we're going to get x minus 4. That's fine. Yeah, so part A is 1. Part B, we have to factor that denominator. So if we set it to 0 and solve, two numbers that multiply to give us 8 are going to be what, like 4 and 2? Let me see. Yeah, because negative 4 times negative 2 is going to be positive 8, and negative 4 plus negative 2 is going to be negative 6. So then it should be 2 and 4. I'm still going to rely on the type notes. We're going to see that in just a moment. Now in part C, if you still got to throw out x equals 2 because, even though when you simplify it down, the x minus 2 goes away, because the original has x minus 2 in the denominator, you still got to throw out that 2, right? So we're going to see that one too. I'm going to rely on my type notes. Okay, so let's take a look at it. So for part A, it's a set of all reals where the denominator is not 0. So in other words, x cannot be equal to 1. So the domain will be everything except 1, and you see how we write it in interval notation. So everything to the left of 1 and everything to the right of 1. Now parentheses in interval notation, that means we get really close to that number, but we never reach it, right? So parentheses when we're doing intervals means we get really close to that number, but we never reach it. So you know, infinity always gets parentheses when we're doing interval notation. Again, infinity symbol always gets parentheses. And then again, in this context, parentheses means we get really close to that number, but we don't reach it. Union just means combine the results from here with the results from here, right? And that's going to give us a complete solution set. So if we take any number from either of these two sets and plug them into the original, they'll work, right? So I think for the second one, we said what, not 4 and not 2. So we had to throw out 4 and 2. It's going to look similar to this, except instead of it being a 1, it's going to be a 2 and a 4, right? So we can include everything except 2 and 4. Let's see, how do we do? So if we set the denominator to 0 and solve, remember we can factor. I think this is what we got when we factored. So then that means that when x is 2 or when x is 4, that makes the denominator 0. So we have to throw those two out, right? And then in interval notation, again, this just means everything except 2 and except 4. I feel like there should be questions. That thing kind of usually gives students a hard time. I think that student's here. Let me check something real quick. Yeah, because I would have marked him as absent. I think he's here. Let me just check real. Let me go ahead and because I remember seeing his name. Let me check again. And this is okay. Let's see if I can find the student. Give me just a moment. Yeah, there he is. Okay, I need to just hover somewhere else. Okay. All right. Right. So again, yeah, if anything is not clear, let me check the chat. Ooh, I don't. Right here. I think the chat looks good. Okay. Okay, my device is like, it's behaving today. It's not throwing a tantrum like it usually likes to do. But hopefully I'm not speaking too soon, because, you know, as soon as you say something like that, it was like, I'm glad you mentioned it. Let me go and throw a tantrum right now. But yeah, so again, with this one, we threw out 2 and we threw out 4. So in interval notation, it's going to look like this. This basically says the solution set includes all real numbers except the 2 and except the 4. Keeping in mind that parentheses means we get really close to that number, but we don't actually reach it. We get really close to these numbers, but we don't actually reach it. Okay. All right, let's look at another one. Oh, and then part C. So now we still have to throw out 2, right? Even though when we simplify, well, yeah, that's really the long and short. We just have to throw out 2 because the 2 is in the denominator in the beginning, right? And so the solution set's going to look like this. Okay. All right, so vertical asymptotes. The line with the equation x equals a is called a vertical asymptote with the graph of the function f if y goes to infinity as x approaches a from the right. Let me do that one more time. F of x is our y. So again, we say that the line with the equation x equals a is called a vertical asymptote, right? If as y goes to infinity as x approaches a from the right. Y goes to infinity as x approaches a from the right. Okay, we're going to see this graph pictorially momentarily. Or we say that x equals a is called a vertical asymptote if f of f if as x approaches a from the left, y goes to infinity as x approaches a from the right, or as x approaches a from the left. Or if y goes to negative infinity as x approaches a from the right, or as x approaches a from the left, right? So this little superscript, these pluses and minus, the plus means from the right, right? These guys means as we approach some number coming from the right. These minuses means as we approach the number coming from the left, right? So if your y goes up to positive infinity or down to negative infinity on either side of this number, then we consider that a vertical asymptote. Okay, so this is what we mean. So notice that, for instance, let's change the color a little bit. So notice coming from the left of a, y goes to positive infinity. See, as x approaches a from the left, y goes to positive infinity. Also, as x approaches a from the right, y also goes to positive infinity, right? The second part, as x approaches a from the left, y goes to negative infinity. And as x approaches a from the right, y goes to negative infinity. Okay. So that's just like some language and like nomenclature, but it's not as complicated as it looks. That's just like a detailed, accurate way that mathematicians like to say that picture, right? Notice that y is going up to infinity in that case, down to infinity in this case. These are two ways that we'll see asymptotes. Here are two more ways that we'll see it. The first one, as x approaches a from the left, y goes to negative infinity. As x approaches a coming from the right, y goes to positive infinity. As x approaches a from the left, y goes to positive infinity. As x approaches a from the right, y goes to negative infinity. Okay. So between either these two or these two, these are the four different ways that we typically would see vertical asymptotes for our discussions. Okay. Hopefully that was okay. That wasn't too terribly bad. Again, I was just reading this so you can know how to read it. If you can read these things accurately, that'll help to paint the picture a lot better. But I don't want you to get too bogged down into these, right? If you could just get this concept of y going to plus or minus infinity, that's the main point there for asymptotes, for the vertical asymptote, right? So then how to locate a vertical asymptote of a rational function? If f of x equals n of x over dx, d of x is a rational function where n and d do not have common factors and a is a real number, real zero of d, then the line with the equation x equals a is a vertical asymptote of the graph of f, right? So long story short, what this is saying, if we have one polynomial divided by another, and after we simplify like any common factors, because sometimes you'll have things like x minus 2 divided by x minus 2 and they'll cancel out. Whenever you have factors that cancel, that's not going to appear in the graph as a vertical asymptote. That's going to appear as a hole or a gap in the graph. Like anything that forces it to be 0 over 0, those appear as holes or gaps in the graphs. But then when you have some number divided by 0 or something divided by something other than 0 divided by 0, those are the ones that appear as vertical asymptotes, right? So that's like a lot of talk. Let's try to see some of this in action. Okay, so here we're asked to find all vertical asymptotes of the graph of each rational function. So the first one looks fairly light, right? Basically, what value of x makes the denominator 0 when x is 1? So that means that we basically have to throw out x equals to 1, and there's going to be a vertical asymptote when x is 1, right? And so our graph is either going to go to positive infinity or negative infinity as we get closer and closer to x equals 1. For part B, notice nothing is going to cancel, but we can factor out that x squared minus 9. Can anybody tell me the factor of that x squared minus 9? Right. So that's a special factoring case, right? Factoring two terms. We got something squared. We have something squared minus something squared. This factors into x minus 3 times x plus 3, right? So what that means is that our vertical asymptotes are going to occur at plus or minus x equals plus or minus 3. Right? Okay. And I think that this one does not factor at all, right? Because if we set it to 0, I think we get non-real solutions. So what that's saying is that the denominator will never be 0, so there's no vertical asymptote for this one. No vertical asymptote. Okay. So let's look at some prepared notes. So we said the vertical asymptote was x equals 1 for part A. Right? No common factors. So the 0 of the denominator is x equals 1. So the line with the equation x equals 1 is our vertical asymptote. All right. So is there a question? Oh, no. Let me see. Okay. Let's keep going. So then for the second one, I think we got the vertical asymptotes occur at plus or minus 3. So we see that the denominator factors into x plus 3 times x minus 3. When you set it equal to 0 and solve, you get plus or minus 3. So then there are two vertical asymptotes, x equals plus or minus 3. And then for part C, we said that it is never going to be 0, right? It's never going to be 0, so it has no real zeros. So the graph of the rational function has no vertical asymptotes, right? So this is just some of the backstory, like getting a sense of what the graph looks like just based on the original function, right? We're trying to paint a picture. This is right now, it's kind of like art class a little bit, but it's just done in an unconventional way. Okay, let's keep going. So here we're asked to find all vertical asymptotes of the graph of each rational function. Okay, yeah, let's work this one out because we got something interesting going on here, right? Okay, so let's start with part A. Now, off the bat, we can go ahead and say that x cannot be 3 off the bat. Now we don't know if it's a vertical asymptote or a whole, but we can safely say that x cannot be 3, right? So now let's expand, or let's factor the numerator. So x squared minus 9, I think we literally just did that one, right? So that factors into x minus 3 times x plus 3, okay? And the bottom is going to be x minus 3, right? So they only asked us to find the vertical asymptotes. What do you notice? You should notice something happening here. All right. This binomial factor cancels this binomial factor. All right. And so this simplifies down. So what this would look like, this is just going to be the line y equals x plus 3, but then there's a hole when x is 3. Right? So even though that canceled in the way that you see, I'm going to say that this basically has a hole. This has a hole at x equals 3. This is not a vertical asymptote. I'm going to abbreviate it as VA. Okay. So yeah, come here. Hey, come here. Come on, come here. She hears noise, so then she loses her mind. A little bit of mind that she had. She's like an alarm system or a guard dog or whatever. So she hears noise, so she just like goes crazy. Let's see. Okay, so we can factor part B. So there was no vertical asymptote in part A, but we did have a hole. The instructions asked us to only find the vertical asymptotes. So, there was no vertical asymptote there. Okay, so for part B, and then it's like, what I've noticed that with like the dog, you have to like growl at them and you have to treat them kind of like you're like the alpha dog. You have to like kind of get into the mind of a dog and like you're like the leader. Like, hey, you need to listen to me. And like you kind of like nip at them a little bit, but you have to like have that like growl. That's the only time when they like really, really listen is like you growl. But I mean, I'm no like Caesar Milan or anything like that. That's just been my experience. But that's neither here nor there. So that's why I kind of like put that little umph in there so she would like listen. That's the only time she really listens to me. Or if I have food or something she wants. But otherwise she'd be like a little gremlin or whatever. Okay. We got a solid 15 minutes, so let's take advantage of it. So now with the second one, let's start by factoring. All right, so x squared minus 4, that factors x minus 2 times x plus 2. And on top, we still have x plus 2. Okay, so what that means now, we can safely say that x cannot be equal to plus or minus 2, right? But because these guys cancel, what that means is that we have a hole. We have a hole when x is equal to what? Negative 2, and the vertical asymptote when x is equal to positive 2, right? So those are the results that we got for that one. And then for the first one, we said there's no vertical asymptote. We had a hole, but no vertical asymptote. Okay. Okay, so let's see, how do we do? Let's compare this to the prepared notes. So we said no vertical asymptote, and then the vertical asymptote was only x equals 2. Okay, so the graph, so for part A, it says the graph is the line with the equation y equals x plus 3 with a gap or a hole when x is equal to 3, right? So I think we said that. And then for part B, and say it's going to look something like this for part A, right? So then for part B, right? We said the graph has a hole at x equals -2, and the graph also has a vertical asymptote at x equals 2, right? Let me make sure that that's what we said. We said a hole at -2, right? Hole, right? Okay. So hopefully we're all aboard and we're not all bored, between the dog losing her mind and me growling at her. You can at least get something. And hopefully this stuff can just sink in. Now, I do want to say I have the full lecture available for this. I think that you all's a copy, the student notes are available. I do encourage you to look at the student notes in advance and try to work these examples from the student notes. The more from the student notes you can do without help, the better. And then once you start getting stuck, then you might want to go and watch the lectures or ask questions in class and fill in whatever's missing, right? So you can have a complete set of notes. You want to be neat and organized. Hopefully also, as you're making your way through the homework, you're getting a copy of the original question, showing all supporting work, and putting your final answer in a box. That's the recommendation, because there's a good chance that you're going to see all of these questions again at some time that's very important in the near future, right? So, but if you're not neat and organized, if you haven't created yourself, it's not going to serve you. If you borrow somebody else's notes or whatever, that's not really going to serve you. The recommendation is to create it on your own, right? That way, you still work together, that's okay, but you want to do as much on your own as you can, right? And so this is a pictorial representation. Did they access the graph? Look at something. Fine. No, they just asked us to find the asymptotes. Okay. All right. So then that was a little bit on vertical asymptotes. So now let's look at horizontal asymptotes. So the line with the equation y equals k is called a horizontal asymptote of the graph of f. Okay, let's do like this. So if y approaches k as x goes to the far right or as x goes to the far left, right? So a horizontal asymptote is going to be like if you look far to the right or far to the left on the graph, then your function approaches some number, then we consider that to be a horizontal asymptote, right? So horizontal asymptotes are concerned with long range or in-graph behavior, either the far right or the far left. Okay. Rules for locating horizontal asymptotes. Okay, let me see. So let f be a rational function given by this. So then, which is basically one polynomial over another polynomial, right? Where the leading coefficients for the top and the bottom are not zero. To find whether the graph of f has one horizontal asymptote or not, we compare the degree of the numerator with that of the denominator, right? Let me see. So there's three tests that we're about to look at. So if we have one polynomial over another, we're going to be comparing this guy to this guy. You can kind of ignore a lot of this, right? When we start to look for horizontal asymptotes, we're going to compare the degree of the numerator to the degree of the denominator. That's going to tell us everything we need to know for the horizontal asymptote. So these are the three rules for locating horizontal asymptotes. If the degree of the numerator is less than, no, you gotta wait, because you don't know how, you act like you don't have the home term. You're like a wild animal, so you gotta wait. Now you gotta sit in timeout until I let you go. I'm holding her in my lap, so that way, she's less likely. She still goes crazy sometimes, but it's drastically reduced. Okay, so the first rule, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is going to be the x-axis, or y equals 0. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is going to be the ratio of our leading coefficients. If the degree of the numerator is larger than the degree of the denominator, then there's no horizontal asymptote, right? Not that this is a formula, but if you have a formula sheet, I probably would include this on the formula sheet. It's not really a formula, but it does come in handy in locating horizontal asymptotes. Okay. Let me pause it. Are there any questions so far? Let me check the chat real quick. Okay, there is something in the chat. You said classes were set up. Yeah. So this is really intended to be a study session. I just fill it with the lecture just because it's easier. But we can talk about homework. We don't have to go through the lecture because, again, you already have a copy of this. So if you want to go through some homework questions, we can. We got a solid 10 minutes before we go our separate ways. So you just have to get my attention and ask me, and I'll stop. Okay. So here's an example. We're asked to find horizontal asymptotes of any of the graph of each rational function. So for horizontal, okay, can somebody, a brave soul, can I get a brave soul to identify the degree of the numerator versus the degree of the denominator in part A? What's the degree of the top? Anybody feel confident in that? So the degree of the top is the variable with the highest exponent, right? So we have this x, so the exponent there is a 1. Same thing for the bottom. The variable with the highest exponent is going to be this guy. Don't get fooled because it's out of order. You have to put it in descending power order. So the degree of the denominator is a 1. The degree of the numerator is a 1, right? So then this horizontal asymptote is going to be 5 divided by -3. It's the ratio of the leading coefficients. And what helps is if you rearrange it so that the terms are a descending power order, right? So this is power of 1, this is x to the power of 0. This is x to the power of 1, x to the power of 0. So it is recommended that you rearrange them and put them in descending power order. So then for part B, so now you should be a little bit more confident. Can I get someone to identify the degree of the numerator? What's the degree there? It's very similar to the first one, right? So the degree of the numerator here is a 1. What's the degree of the denominator? It's a 2, right? So this is the first case where the degree of the numerator is less than the degree of the denominator. So this horizontal asymptote is going to be y equals 0. Y equals 0 for this one. This one, the degree of the numerator is larger than the degree of the denominator. So there's no horizontal asymptote for them. Okay. So we said the first one was 5 over -3. Then we got y equals 0. And then we got no horizontal asymptote. So you see the -5 over 3. I think we said y equals 0 for part B. You see it here. And then for part C, we said no horizontal asymptote. Okay. And those are basically just direct applications of those 3 rules that we saw just a moment ago. Let's hang out for like another 5 minutes. Let's go as far as we can for the next 5 minutes. Now, let me think about this one. This is going to be our last one. Okay. So we're asked to sketch the graph. Let me see. Let's start by factoring, right? I'm not necessarily going in the order which the text is doing it. I'm just trying to cover my bases. Don't want to give myself some space. Let me give myself some space. No, you can't do that. Let me give myself some space. And with 5 minutes left on the clock, I don't know that I'm gonna be able to do this in 5 minutes, especially if my device is like acting up like it is. All right, that's good. Okay. And then I can drop that right here. And let me add a page. This one, page. Okay. So let's just take a moment and try to get through. Come on. There it is. Oh, part of it is I've noticed also when I have my tablet plugged in, it doesn't behave properly. So I just unplugged it. Hang on, give me a second. I'll be right back. There it is. Okay. Well, that was such a pain. Okay. So we're actually sketch the graph. So now there's a set of steps that I personally like to follow. First, I like to identify any intercepts. Right? Let's do that one first. Let's identify any intercepts. And I personally like to start with the y-intercept. Right? So to find the y-intercept, we set x equal to 0. So if we set x equal to 0, I think we get a y-intercept of a positive 2/9. So when x is 0, y is 2/9. Okay. Let me see the x-intercept. So for the x-intercept, we would set y equal to 0, but a fraction is going to be 0 when the numerator is equal to 0, right? So if we set the numerator to 0 and solve, we should probably identify the domain as well. We'll do that in just a moment. If we solve from here, add 2, divide both sides by 2, we get x squared equals 1. So the x-intercepts, we get x equals plus or minus 1. You take the square root on both sides. So then we get 1, 0, and we also get negative 1, 0, right? So we got our x-intercepts. Now, before I go forward, let me identify my domain. And what I want to do, I want to go ahead and factor. Let me see. I want to factor the top and the bottom. I'm watching the clock. I got a couple of minutes. Now, if I factor out 2 from the top, we're going to have x squared minus 1. So that factors into x minus 1 times x plus 1, right? So that's the factored form at the top. The bottom, we have x squared minus 9. That factors into x minus 3 times x plus 3, right? So this is saying that x cannot be plus or minus 3. Okay, so I think we're okay. So now, and let me do these guys in purple. And these are also like notes, so we can do like this, just to create some contrast. Oh, and then this, right? So when we found our x-intercept, we set the numerator to 0. So then the next logical flow or natural flow for me is to go ahead and set the denominator to 0. And so when you're setting the denominator to 0, we're considering any. So next we want to consider our asymptotes, right? So then for the vertical asymptote, we're setting the denominator equal to 0, right? So I don't think we have any holes or gaps because nothing canceled. If we set the denominator to 0 and solve, I think we get vertical asymptotes of x equals plus or minus 3, right? So at plus or minus 3, we're going to have vertical asymptotes. If we want to consider the horizontal asymptote, we have to compare. You gotta. I didn't say anything. I just realized that my screen wasn't sharing. That's okay. You gotta like say something. All right, let me try to finish this out. So, we're about to get out. Okay. So you're just gonna have to listen to the audio and backtrack to try to fill all this in, because we're out of time. Stop. Just stop. Because you're being too much. So for the horizontal asymptote, let me make a note here. Horizontal asymptote. That's why I was like, we might not have enough time. But we want to. So if we talk about the vertical asymptote, we can also talk about any horizontal or oblique asymptotes. So here, if we compare the degree of the numerator to the degree of the denominator, they're equal. So this is like case number 2. So that's going to be the ratio of the leading coefficients. So we have a horizontal asymptote at y equals 2. That's going to be y equals 2, right? Now, normally what I would do is I'm just going to abbreviate it. I'm going to say 3. I'm going to say a few additional points between your vertical asymptotes and your x-intercepts. So I'll just do that quickly, all right? So say this is the positive x. Let me see, the x-intercepts, we got plus or minus 1. So it looks like we have 4. 1, 2, 3, 4. I know we had negative 3 and positive 3. And then we had plus or minus 1, right? Now, these were vertical asymptotes. And these were zeros, or the x-intercepts. So then I would find points basically between and beyond all x-intercepts and vertical asymptotes. So I would find a point here, a point here, a point here, a point here, and a point here to plot on the graph. And then the final thing I would do was put all this together in a graph, right? We're kind of out of time, so that's the only reason I'm not doing it. But for the graph, I would just put all of these results together. All right, and let me highlight the results. So we got a y-intercept here. We got two x-intercepts here. We got two vertical asymptotes here. We got a horizontal asymptote here. And then we have 5 additional points that we would include. We would just choose an x, find the corresponding y, and then you put it together. And I mean, I wanted to do it without the notes, but we're out of time, so I'm just going to rely on my notes. But when you put it all together, it's all here. So just notice, here's the vertical asymptote. There's one there and one there. We said x-intercepts of plus or minus 1, so you see those there. We got our y-intercept of 2 ninths. You see it there. And then notice they also have those additional points. Here's an additional point. Here's an additional point. I mean, that one's already there, but here's an additional point and here's one, right? So hopefully, well, I don't really intend to come back to this section. I did kind of want to put it together and show you how to graph that. But again, I think I do have that in my pre-recorded lecture. But with that, we are out of time. Go ahead. All right. Did anyone want to ask any questions before we go our separate ways? Any questions? Okay. So, rational functions is just one of those things. You just have to do the best you can. One of the biggest challenges there is factoring. So, that takes practice. If you want more practice on factoring, I do have a section in our handouts on Blackboard that has a whole chapter devoted entirely to factoring. Plus, there's a PDF that's a quick summary of how to approach a factoring question. That is something that you're expected to know in this course, but I know we all are aware that gives many students a hard time. Let me just hop back over to Zoom really quickly. I know we kind of lost. I think he's probably for the next class. I'm going to assume he's for the next class. Inverse functions. Explain, but I need more help understanding the concept. Yeah, the screen had blocked out. It's okay. So with inverse functions, I mean, only because we're out of time, you're going to have to link up with the tutors. For me to kind of help outside of class. So as you're going through the homework for any homework section, click on the Ask My Instructor, and it'll send me a screenshot of your question. I'll load it to my device, and I'll make a video response as soon as I can. I kind of, when I'm not with you guys, I'm ripping and running, but I can make a video response and load that to YouTube and send you the link. So that's one way that I am able to but yeah, I definitely, this is why I encourage you all to work together. I also encourage you to seek out the tutors. It's okay if you take this, take your tablet and link up with the tutors. And if you wanted to sit down side by side, I totally encourage that. It's totally okay. But if you want my input, then you would have to use the Ask My Instructor or Ask Me during class. Again, you just got to stop me. Don't let me go through the lecture, because if you let me, I'll go to the lecture. But if you want to work on a homework question, you just got to get my attention, okay? So hopefully we can devise a plan, to kind of get this stuff done. So today we went through as much of section 2.5 as we can. Again, the lecture is there. This homework assignment will be due this upcoming Sunday night at 11:59 p.m. going into Monday morning. Keep in mind, with all of our assignments, we get unlimited attempts, and you can work on any assignment past the due date with only a 10% late penalty. Okay, with that, if there aren't any other burning questions, I have that at this time. We're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Play hard, but work hard and play hard. So be sure to get your assignments done, but then get out and explore Atlanta. I don't know if you guys are in the city or not. I know you can often find me on the Beltline running. I might have my dog with me. I love the Beltline in the city of Atlanta. It's so much fun. The energy is it's such good energy. I don't know if they've started it back yet or not, but pre-COVID, on Sundays at 6:30 at Old Fourth Ward Park, there was free yoga in the park. So if you can find your way just to explore the city and do what you got to do, get your work done. But it is important to balance, have a balanced work play life. So get outside and play, get some fresh air. I'm an advocate for nature. I love nature. Okay, guys? All right. Get it done. Do your best. Forget the rest. Don't stress and be blessed. Take care. Enjoy your weekend. And from one beautiful mind to another, take care. Peace. All right. So let me reboot everything because I know. Let me see. You as well. You as well.